In this video, we are going to review different types of chemical formulas that are commonly used in organic chemistry. First type of formulas we are going to look at are complete structural formulas. A complete structural formula, as this one, represents all the atoms and all the bonds in the molecule. No abbreviations are used. This formula shows connectivity, which atom is bonded to which one, and with what type of bond, whether bond is single, double, or triple. In a complete structural formula, no stereochemistry, and stereochemistry is arrangement of atoms in space, so no stereochemistry is indicated or implied. Lewis formulas that you have already seen are complete structural formulas. Here is another example of a complete structural formula. You can see it shows molecule very well, but drawing is a bit cluttered, and also it takes quite a bit of space and takes time to draw if you are doing it by hand or typing it. So we have various abbreviations, and one common abbreviation is condensed structural formula. Condensed structural formula doesn't show carbon-hydrogen bonds. Hydrogen is monovalent, can form only a single bond. So drawing carbon-hydrogen as a single bond is redundant. It shows redundant information. We should know that that bond is single bond. So for that reason, in a condensed formula, as name indicates, with condensed formula, so that we don't show carbon-hydrogen bond. And so this is an example of a condensed structural formula. Now, we can also omit carbon-carbon single bonds. Here is another example of condensed structural formula. Those are condensed structural formulas of compounds above. We can actually also omit drawing carbon-carbon single bonds. So both types shown here are acceptable. So we can either condense only carbon-hydrogen bonds and still show carbon-carbon single bonds, or also condense carbon-carbon single bonds, and simply understood that bonds between carbons, if they are not shown, are single bonds. Both are acceptable, and you can see when typing, particularly in a line of text, it may be convenient to omit single bonds. We could represent them, but again, they don't provide any additional, any useful information. Of course, double bonds and triple bonds must be shown. Otherwise, you wouldn't know that those bonds are there. So this is one example of how you type it in a text, or we can also show those bonds along with single carbon-carbon bonds. Either way, it's acceptable. So there is some flexibility when drawing condensed structural formulas. Now, you should also be familiar with various abbreviations. Particularly in the past, condensed structural formulas were used a lot in text, in a line of text. And you need to know how to convert that formula from a line of text into a condensed formula that shows carbon-carbon single bonds. So you can see it here. You can see one example here where we have branching. So note how branching has been shown. We have second carbon in a chain that is branching. So methyl group is attached to it. So actually, these two methyl groups are shown as in line of text as methyl groups in parentheses. So these pairs of methyl groups correspond to each other. Here is another example. We have a 5-carbon chain, pentane, and this is 3-methylpentane. So note how 3-methylpentane is shown as when it's typed as a line of text. So the methyl group on carbon 3 is this methyl group in parentheses. So you need to know how to convert one formula into the other. So if you're given one formula, you should be able to convert it into the other. So if you're given top formula that shows carbon-carbon single bonds, you should be able to convert it into a line of text. Or if you are given formula from text that contains groups in parentheses, how to convert it into a condensed formula that shows carbon-carbon single bonds. Here is another example with ethyl group. So in this case, we have heptane, and on carbon 4, there is ethyl group as a substituent. And you can see where this ethyl group is in parentheses in a single line formula. And yet another example Now we have hexane. It's 3,3-dimethyl hexane. So on carbon 3 there are two methyl groups. And these are two methyl groups. And note how in text they are represented as CH2 in parentheses 2 times, or CH3 twice. Complete structural formulas and condensed structural formulas don't indicate arrangement of atoms in space. For that, we have perspective formulas or perspective drawings. So a perspective formula, here is an example of perspective formula of butane, first represents carbon chain as zigzag chain. That is done to approximately represent tetrahedral angle. So all the carbons in a chain are part of zigzag chain, and two terminal or end hydrogens are part of the same chain. So those atoms are in the plane of the drawing. Any atom that is projecting towards the viewer is shown as attached to carbon in a chain by a wedge bond. So a wedge bond is projecting towards the viewer, and dash bond away from the viewer. This can be compared with model of butane. So you can see how this drawing on the right, perspective formula on the right, that involves solid bonds that are in the plane of the drawing, wedge bonds projecting towards you, and dash bonds away from you, how they correspond to atoms in a model. How carbons into terminal hydrogens correspond to this zigzag chain, and how on each carbon we have one hydrogen projecting towards the viewer and one away from the viewer. Make sure when drawing these formulas that you represent the tetrahedral atom correctly. So here is a model of the tetrahedral atom on the left and correct representation. So for example, if two bonds in the plane of the drawing are pointing down, then those bonds that project towards and away from you will be pointing up. That's correct representation of the tetrahedral atom. Middle one is wrong, where all four bonds point down, and students usually recognize that this is wrong. But one on the right is what students will often draw without recognizing that that's wrong, that structure is wrong. Bonds that project towards the viewer and away from viewer has to be either both up or both down. They cannot be one up, one down. That's not a tetrahedral atom. We cannot make a model from this formula, and we cannot draw this formula from a model. So correct representation is one on the left, or that one on the left upside down. So if two bonds in the plane of the drawing are pointing down, as in this case, then those that project towards and away from viewer have to point up. Alternatively, if two bonds in the plane of the drawing point up, then two bonds that project towards the viewer and away from viewer have to point down. Also note, in perspective drawing, we actually cheat a little bit when drawing the formula, because really in perspective drawing we should be viewing at the molecule like this at the bottom. So we should be looking at the molecule from the side, and we should only be able to see substituent, in this case hydrogen atom, that projects towards us, towards the viewer. And that one would be eclipsing one at the back that projects away from the viewer. But that's not acceptable, because we have to show all the atoms, in this case hydrogen atoms, that are bonded to carbon. Otherwise we don't know how many atoms are bonded to carbon. So all the atoms have to be represented. But if one at the back cannot be seen, then it's difficult to represent it. So we cheat a little bit and we twist the molecule a little bit. So we turn the molecule to the side just a little bit so that all the atoms are shown. So you see, this is the actual view, but this is actually how we cheat and twist molecule a little bit so that we can represent all the atoms. So if you are using models to make model from a formula or to draw a formula from a model, you have to turn it just a little bit so that you can see all the atoms. So that's the actual model. There is one other important point when drawing perspective drawings. And again, we'll use butane as an example. You have to be consistent with drawing wedge and dash bonds to represent molecule correctly. So note how we have turned molecule slightly to the left so that we can see both hydrogen atoms that project towards the viewer and those away from the viewer. So to draw them correctly, we have to use wedge and dash bonds consistently. So note how on each carbon, those hydrogen atoms that project towards you are in this case to the right, and those away from you to the left. What that means is when you draw a formula, since you're representing those that project towards you with a wedge and away from you as a dash, on the first carbon, left carbon, let's assume that's the first one, wedge points to the left and dash to the right. That means on all other carbons, wedge bond has to point to the left and dash to the right. That's consistent representation and is correct. So that's correctly drawn perspective drawing. A perspective drawing where you are mixing up wedge and dash representations where they randomly point to the left and right is wrong. That simply doesn't show a molecule that is turned just slightly to the left or right to show all the bonds. For cyclic formulas, we also use perspective drawings, and typically for cyclic compounds, we draw a ring in the plane of the drawing, so all the bonds are in the plane of the drawing, and only to indicate stereochemistry, those above the plane of the drawing, above the plane of the ring, are indicated as wedge, and those below as a dash. So on the left here, we have 1,2-dimethyl cyclobutane as Lewis structure or condensed structural formula, and on the right as perspective drawing, showing that both methyl groups are above the plane of the ring, and on those carbon atoms 1 and 2, both hydrogen atoms are below the plane of the ring. We can also combine this with line formulas. We'll cover line formulas in a minute. So we often draw rings as line formulas. When we draw rings as line formulas, we can combine that with perspective drawings and end up with perspective line formulas. So here are examples of perspective line formulas where wedge and dash bonds are used to indicate stereochemistry of substituents. Note that for those bonds at the end we can put substituents like CH3 methyl and hydrogen. We sometimes do that simply as a courtesy to the reader. That's optional, and often we omit them, as you can see in other examples, in the remaining 3 examples. I just mentioned line formulas. They are used a lot in organic chemistry, and you need to know them really well. You need to know how to draw them, what they represent, and to convert line formulas into different types of formulas, other formulas, like perspective drawings or condensed structural formulas, and vice versa. Convert perspective drawings or condensed formulas into line formulas. Line formulas are the ultimate in condensation of a chemical formula. So previously we condensed structural formula by not showing carbon-hydrogen bonds because they are single bonds, that's redundant information, and also not showing carbon-carbon bonds when they are single bonds. Line formulas are condensed a little bit differently. First, we show carbon-carbon bonds. So any bond that is shown is assumed to be carbon-carbon bond. But, as you have already seen, we can omit carbon-hydrogen bonds because that bond has to be single bond. Well, we also figured out that we can also omit hydrogens because carbon has valence of 4. So if we draw all the substituents on carbon except for hydrogens, then we can easily deduce how many hydrogens are left. So if carbon forms a single bond, if we represent carbon as forming just one bond, a single bond, that means that remaining 3 substituents on carbon are hydrogens. And so in these 2 examples shown right here, we have just a single bond. So line formula, or this line on the left, indicates that 2 carbons are bonded to each other by a single bond. And that's all. So since each carbon forms only a single bond, that means that each carbon also has 3 hydrogens to satisfy its valence of 4. So this formula is CH3 attached to CH3, or formula of ethane. Formula next to it shows 2 carbons bonded to each other with a double bond. That means that each carbon is also bonded to 2 hydrogens. So this is CH2 bonded to CH2, or ethene. Next, we have line formula of cyclohexane, and in fact, line formulas were originally introduced to represent cyclic compounds because they are so convenient for representing cyclic compounds. So each carbon forms 2 bonds in cyclohexane. That means that each carbon represents CH2 group. Remaining 2 bonds have to be 2 hydrogens. Next compound is 4-methylheptane. So you can figure out substitution of each carbon. If you start at the left, that will be CH3 because that carbon forms only 1 bond. Next 2 carbons will be CH2 each because they form 2 bonds each. Middle carbon, carbon 4, is CH. Carbon attached to it is CH3, and then we have remaining CH2, CH2, CH3. Here are some additional examples. With double bonds, we may have to show whether substituents are on the same or opposite sides of double bond. That's so-called cis-trans isomerism that we'll cover later in the course. So note that double bond is also represented as part of zigzag chain, and 2 substituents, in this case 2 carbon-carbon bonds, carbon-carbon single bonds that are on the double bond, are on the opposite sides of double bond. You will learn more about it when we cover alkenes. At this point, you only need to be aware of it. And finally, triple bond is not part of a zigzag chain. Students often make that mistake and represent triple bond as part of zigzag chain. Triple bond is linear, and so we represent it as being linear. So 2 carbon-carbon bonds or any other bonds attached to triple bond are part of linear geometry of triple bond. So they are drawn linearly, and make sure you draw it that way. Finally, there are 2 types of formulas that are very useful when one wants to represent conformation or stereochemistry, either way, 3-dimensional arrangement of atoms in space. But at this point, those formulas may not make that much sense to you. So don't worry if you don't quite get them right now. We'll cover them in more detail very soon. If you can figure them out now, and if you understand what they represent, that would be great, but if not, don't worry too much. So first type are Sawhorse formulas, and they are very useful if one wants to represent stereochemistry on the 2 neighboring carbon atoms. So for example, in butane, on the left you have perspective drawing that you are already familiar with, and Sawhorse formula of the same molecule of butane, same representation, same arrangement of atoms in space is shown on the right, and carbons 2 and 3 are shown. So Sawhorse formula would be used if one wants to represent arrangement of atoms in space on carbons 2 and 3. So you can see then we draw that bond 2,3 as being unusually long, and substituents on carbon 2 and 3 are drawn in a form of either inverted letter Y or letter Y. So drawing on carbon 2 is inverted letter Y, and drawing on carbon 3 letter Y. So you may be able to figure out how they correspond to substituents on carbons 2 and 3 in perspective drawing, and if you make a model, you may be able to make more sense out of it. As I said, we'll be covering those formulas in much more detail in this course very soon. Another very useful formula is Newman projection formula. It is also used to represent stereochemistry on the 2 neighboring carbon atoms, or 2 atoms in general. But now we look at molecule along the carbon-carbon bond. For example, C2-C3 carbon. And then we represent molecule in such a way that we only see the closer carbon atom and not, well, actually closer carbon atom is represented as a dot. So this closer carbon atom is the dot from which 3 bonds are projecting as a letter Y. And then back carbon atom is represented as a ring. So we don't see the bond between the 2 atoms. It's simply along the line of view. So back is represented as a ring. You see it right here. And then above the horizon of that ring, bonds, in this case carbon-hydrogen bonds, appear. So that would be in this case inverted letter Y. And so you can see in this case molecule of ethane and 3-dimensional arrangements of atoms in space of molecule of ethane. Also very useful representation called Newman projection. But again, if it doesn't make much sense to you at this time, don't worry about it. It's less commonly used to represent molecules like ethene. I use it here only to show that, again, as in case of perspective drawing, when atoms are eclipsing each other, we have to cheat a little bit and twist the molecule a little bit to the left or right, or in this case, a little bit down, move atom closer to us a little bit down, so that we can see all the substituents, both on the front atom and the back atom. So we adjust the formula a little bit. This completes our review of chemical formulas that are used in organic chemistry, and next we'll be doing introduction to organic nomenclature.